Welcome to Physics Chapter 6, Lecture Number 1. We're going to cover on your own problem 6.1 to 6.4. The first problem that we will work together is on page 184. If you want to go ahead and turn to that. But let's start out with our notes. So this section is called Applications of Newton's second law. Remember, that's F equals ma. So first we want to talk about equilibrium. And what is translational equilibrium? Well, that's when the sum of all the forces acting on an object is equal to 0. There's two types of translational equilibrium. The first is static equilibrium, and that's when the object is at rest. The second is dynamic equilibrium, and that's when the object moves at a constant velocity. Remember in Chapter 5 we worked some problems where the object was at rest, we were trying to get it broken loose, and where the object was moving at a constant velocity. Now a new concept is called tension, and that's the force directed away from the object being supported. So I've left you a little space to do a drawing here, and let's think about maybe the light fixture above, say, a kitchen table. Okay, so in this space, so we'll do this. This is like the ceiling, and we have some sort of chain or something like that that holds the light fixture up. We'll draw just kind of a simple light fixture. All right. Now, the weight, to do kind of a free body diagram, is going in the downward direction. So the force directed away from the object would be tension. Okay, so there's tension in this supporting chain that keeps the light fixture from falling to the floor. So if we were to analyze this, if up is the positive direction, tension minus weight has to be 0 if this is in equilibrium. If it weren't 0, then the light fixture would either be falling down or going up. So the tension in this case is just equal to the weight. That's not always true, but in this simple case, that's what's going on. And we're going to work an elevator problem in 6.4 that's really kind of like this. Okay, it's just an illustration of this. All right, so let's move on in our notes. So to solve these problems, we set the sum of the forces in each direction, or each dimension, both the x and y, equal to 0. And we use simultaneous equations, so that's something you did in algebra and in pre-cal, to solve for each unknown. Okay, so let's turn in your book to page 184. And we'll work through this first on your own problem. All right, so this one says, two farmers are trying to pull a mule into a barn. That's just not going to work. The mule does not want to go, so she is pulling back against the farmers with a force of 2 times 10 to the third newtons, or 2,000 newtons, including the effects of friction. If the farmers are pulling as illustrated below and the mule does not move, what is the tension in their ropes? Okay, so on these types of problems, what we want to do is draw a free body diagram. So we've got the mule pulling like this with a force of 2,000 newtons. Then we've got a farmer pulling like that. We don't know what the tension is. I'm just going to call that one T1. And then we've got another farmer pulling like this. It's farmer 2, so we'll call that T2. We want to solve for both T1 and T2. Now, from a geometry standpoint, we know that there's a 45-degree angle here and a 45-degree angle here. So what we have to do is, if this is in equilibrium, and it is, it's a stalemate, the sum of all the forces in the x direction have to be 0. Same is true for the y direction, but first let's do x. So what we're going to do is, and remember your angles here, coordinate plane, we have 0 degrees, 90 degrees, 180 degrees, and 270 degrees. So we have to put our angles in that way. So I'm just going to go around the world here, right, around the circle, and analyze each force. So we have T1, and remember cosine goes with x, so times the cosine of 45 degrees, plus, we know the force here, 2,000, times the cosine of 180 degrees, plus T2 times the cosine not 45 degrees. Remember, we're coming all the way around to here, right? So that's 315 degrees. And because it's in equilibrium, it's equal to 0. So you're just going to put cosine 45 in your calculator, right? So just cosine 45, if you're make sure you're in degrees, it's 0.707. So we'd have 0.707 times T1 plus, now the cosine of 180 degrees, you can put that in your calculator, but it's -1. So that's 2,000 times -1. So minus 2,000 plus, if you put cosine of 315 in, you will get that is also 0.707. All right, so cosine 315, 0.707, because cosine's positive in the fourth quadrant. So plus another 0.707 T2 is equal to 0. So we're kind of stuck there, but I'm going to put that negative 2,000 over to the right. So I'm going to have 0.707 T1 plus 0.707 T2 is equal to 2,000. Now let's analyze this thing in the y direction. We know it also has to be 0. Now, which trig function goes with y? Remember from chapter 2 and chapter 4, it's sine. So we'd have T1 sine 45 degrees plus 2,000 sine 180 degrees plus T2 sine 315 degrees. Again, we're just going around the horn. This time we're doing analyzing the forces in the y direction. Have to be equal to 0. If it's not equal to 0, they're moving. Okay, sine of 45, you put that in your calculator, it's also 0.707. So you'd have 0.707 T1. Now the sine of 180 is 0. So the 2,000 times sine 180, if you're not sure, I'll show you. Sine 180 is 0. So that's nice. That goes away. And then the sine of 315 degrees is negative 0.707. So sine 315, you can see, negative 0.707. So I would have, this part goes to 0, and then minus 0.707 T2 is equal to 0. So 0.707 T1, if we move that T2 over to the right, is equal to 0.707 T2. So if we divide both sides by 0.707, we would just have T1 is equal to T2. I kind of hope that makes sense to you, since they are basically pulling at the same angle from the x-axis, that the two would be equal. Now, if they weren't at the same angle, they wouldn't be equal. Now we're going to do a substitution. we're going to substitute T1 in for T2. So I'm going to do that right here. All right, we know that T1, so let's look at this equation right here. 0.707 T1 plus, remember T1 and T2 are interchangeable, so we can say 0.707 T1 again, because T2 is equal to T1, is equal to 2,000. So if we add those two together, that's 1.414 T1 is equal to 2,000. Now we can get T1. So T1 is 2,000 over 1.414, and that is 1,414.4 newtons. And that's also equal to T2, remember, because T1 is equal to T2. All right, so pretty cool problem. A little longer, certainly a lot longer than those Chapter 5 problems, but interesting, and you get to use your Algebra 2 and your Pre-Cal where you did substitutions to solve things. All right, so let's pause the video if you need to and move on to 6.2. All right, 6.2 is just on the next page, page 185. So it says 112.1 kilogram sign is hung from two strings as shown below. What's the tension in each string? Okay, so first of all, I need to get the weight of that sign. So weight is mass times gravity. It's a really heavy sign, 112.1 kilograms times 9.8 meters per second squared. All right, if you run that through your calculator, you're going to get that is 1,098.6 newtons. All right. So now let's draw the free body diagram. So we've got the ceiling here. So I'm just kind of redrawing the diagram from the book. And we've got something like that. Really a dumb way to hang a sign. Something like that. And then the sign is going straight down, and that's 1,098.6 newtons. And we know that with respect to the x-axis, it shows that this is 50 degrees and that this is 35 degrees. Now, you can name them what you want, but I'm going to call this line T1 and this line T2. And we're going to do the exact same analysis as we did in 6.1, except this time those two, since they're different angles, T1 and T2 will not be the same. So it's going to even be a little more math to deal with. So we have the sum of all the forces in the x direction. Because this system is not moving, it's in equilibrium. So it has to be equal to 0. So remember, x goes with cosine. So T1 cosine 50 plus T2 cosine. Now it's not 35, is it? Remember, we're starting at 0 degrees here and we're going around to here. All right, 35 degrees away. So that would be 180 minus 35 degrees, which is going to be 145 degrees. Plus, and then we have here going straight down 1,098.6 times the cosine of 270 degrees equals 0. All right, cosine of 50, you put that in your calculator, it's let's see, 0.643. And then a cosine of 145 is negative 0.819, so minus 0.819 T2. And then the cosine of 270 is actually 0. You can put that in your calculator and test that. That's 0. So that is equal to 0. So I'm going to shove this T2 over to the right. I'd have 0.643 T1 is equal to 0.819 T2. Let's solve for T1. It's 0.819 over 0.643 times T2. So T1 is equal to 1.27. That's 0.819 over 0.643 T2. So we have a relationship between T1 and T2, and we can do a substitution in a little bit. So let's look at the y direction. We're going to go through the same process. We're just going to substitute cosine with sine. So T1 sine 50 plus T2 sine 145 plus 1098.6 times the sine of 270 equals 0. Now the sine of 270, you can put that in your calculator, but it's negative 1. Sine of 50 is 0.766. Sine of 145 is 0.574. And then we'd have negative 1 times 1098.6. That'd be minus 1098.6 equals 0. Let's go ahead and move that minus to the right side. So equals 1098.6. Now I'm ready to do a substitution because we know that T1 is equal to 1.27 times T2. So we have 0.766, and I'm going to substitute 1.27 T2 in here for T1. So plus 0.574 T2 is equal to 1098.6. So 0.766 times 1.27 would be 0.973. All right, add those two together, and you'll get 1.55 T2 is equal to 1098.6. So T2 is equal to 1098.6 over 1.55. And that's going to be 708.8 newtons. So I have one of them. How would I get T1? It's not hard. All I have to do is plug that 708.8 right in here for T2. So T1 is equal to 1.27 times 708.8. All right, and therefore T1 is going to be 900.1 newtons. Now I could have done it the other way. All right, sorry about my circle getting too big there. That's 1.27 times 708.8. I could have done it and solved for T2 is equal to 0.643 over 0.819, right? And I'd have a relationship of something equals T2 there. And you would have, your first answer you would have gotten would be T1 at 900.1 newtons, and then you would have plugged in to get T2. But you get the same answer. All right, well, pause the video if you need to. Pretty long problem there. And we will do 6.3. All right, so right underneath, this one isn't quite as long. So we have a fish. Fisherman is displaying his prize catch by hanging it as illustrated below. The horizontal string in the hanging apparatus is weak and will only be able to stand a tension of 13 pounds before it breaks. What is the maximum weight for a fish to hang on this system? All right, let's do a free body diagram. Okay, so we've got the, if we just kind of make that the center point there, we know we've got the weight of the fish going down like that. We know that the tension in this string is 13 pounds. It's got a force of 13 pounds going to the left. And then we can call this T1, and we know that it is at 40 degrees with the horizontal. Okay, let's do the sum of all the forces in the x direction. Has to be equal to 0 or the fish is falling down or floating up in the air. Okay, we have T1 cosine 40 plus 13, right? We're coming over to this one. I'm just going in the counterclockwise direction. 13 cosine, what angle is that at? Well, if this is 0 here at the bottom, that's 180, right? Cosine 180 plus the weight of the fish times the cosine of what? 270 equals 0. Well, I know let's see, cosine of 180 is -1, so this is 0. Right? You can put that in your calculator. Cosine 270 is 0. Cosine of 40 degrees is 0.766. The cosine of 180 is -1, so minus 13 is equal to 0. So 0.766 T1 is equal to 13. So T1 is equal to 13 over 0.766, which is 16.97 pounds. All right, so I know T1, 16.97 pounds. Now let's look at the y direction. So I'd have T1 sine 40 degrees plus 13 cosine 180 degrees, not cosine, so sorry, sine. Remember, we're substituting sine for cosine, plus W sine, and that T1, I'm sorry, T1 is 16.97. Plus W sine 270 degrees equals 0. So we know this is -1. 16.97 times the sine of 40 degrees, and sine of 180 is 0, so this whole thing goes away. So 16.97 times the sine of 40 would be 10.89. And then since that's -1 times W minus W equals 0, so 10.89 pounds is equal to the weight. All right, sorry that I had to make a few on-the-fly corrections as we went through that one. But less work than the first two, for sure. Okay, let's do 6.4 and then we'll be finished. If you'll just turn your notes over to page 3, we're just going to do the top of that. And in the book, you'll be flipping several pages over to page 188. All right, so 6.4 says that a spherical mass of 50 kilograms hangs from a string in an elevator as illustrated in the drawing to the right. The tension in the string is 460 newtons. Remember, that would be directed upwards, away from the weight. What is the acceleration, magnitude, and direction of the elevator? And from this information, is it possible to tell whether the elevator is moving up or down? Why or why not? Okay, so We did one of these in Chapter 5, so let's just draw a free body diagram here. We've got a spherical mass. We know that the tension in the string is 460 newtons. Now the weight of this mass is directed downwards. Weight is mass times gravity. That's 50 kilograms times 9.8. So that's going to be 490 newtons directed down. We don't have to worry about any friction here or anything. So the summation of all the forces is equal to mass times acceleration. Remember, this is applications of Newton's second law. And let's say that up is the positive direction. So I would have 460 newtons going up minus 490 newtons going down is equal to 50 kilograms times acceleration. So negative 30 newtons is equal to 50 kilograms times acceleration. So acceleration is going to be negative 30 newtons over 50 kilograms. And that's going to be negative 0.6 meters per second squared. All right, so meter per second squared is the same thing as a Newton per kilogram, isn't it? All right, the second part of the question is, from this information, is it possible to tell whether the elevator is moving up or down, and why or why not? Well, I want you to think about that a little bit, but the answer is no on part B. Because the elevator could be going up. Remember, the weight is greater than the tension of the string. So if you're riding on an elevator, you know how when you're going up, but suddenly the elevator suddenly starts to slow down at the end, that you feel like you're floating in the air just a little bit? Or if you do that on a roller coaster or something like that, you could be going up, but slowing down. So that's one way to get the tension in the string less than the weight. Or you could be going down but speeding up. If that's the case, like when an elevator first takes off and it's going down, you feel like for just a moment in time you're floating. All right, that's because the elevator is moving faster because of inertia, and you haven't caught up with it yet. So the tension in the string for this mass would be a little bit less than the weight if you're going down and speeding up. All right, that does it for today's lecture. The homework that goes with this lecture is going to be review questions on page 214. Look at us go. You can do 1 through 4 and practice problems on page 215. You can do 1 through 3. All right, pretty long lecture today, so sorry about that, but tomorrow's will be much shorter, and I will talk to you next time.